I was thinking back to previous TFAWS, and I don't recall ever seeing a presentation that covers thermal modeling of the human body. And this does relate to aerospace and space applications, because the presentation will also cover how this is used to cover to model astronauts in spacecraft. And our presentation today is by Goluvev. He's a research scientist. He's going to be talking about his thermal model.
Thank you for attending this session. The agenda of my talk, I will first introduce Thermoregulation and our software, and then I will give a comprehensive overview of the Taitherm human thermal model. After that, I will describe a case study that's very relevant for aerospace, which was the validation of the model for assessing the crew-induced loads in spacecraft. So Thermoregulation, we are a software company that provides engineering software and services for many industries, such as automotive, architecture, aerospace, electronics, and textiles. Our main office is in Calumet, Michigan, in the Upper Peninsula of Michigan, and our second largest office is in the Detroit area, and we also have distributors in Asia and a few small offices in Europe. We offer a CAE toolbox consisting of two main software, Taitherm, which is a three-dimensional heat transfer solver, and we have extensions available to model batteries, exhaust, drive cycles, and human thermal physiology and comfort, which is what I'm presenting on today. We also offer Taitherm, which is an automation software that allows to automate multiple Taitherm runs and couple them with user-written Python routines, and or couple with 3D CFD software or 1D system simulation tools. So now I will describe our human thermal model. Many of the historical thermoregulation models, such as the Wissler and 41 node man, also known as MetMan, that are used by NASA are based on treating the human body as a set of cylinders, as shown in the pictures here. Thermoregulation has developed a human model that uses more elements and layers than these historical models, and it's been validated with human subject and sweating mannequin tests, and also allows for local sensation and comfort predictions. So our model consists of 20 body segments with layers representing tissues, such as the bone, muscle, fat, and skin. And note that while these 20 segments are what we use to calculate the physiological behavior, there can be multiple geometrical elements within each body segment, so that provides a high-resolution thermal solution. The model solves the bioheat transfer equation shown here. This equation consists of the thermal diffusion equation with the effects of the metabolism, environment, and blood perfusion considered through the imposed heat rate terms on the right-hand side. And these heat rate terms can vary significantly over time, depending on the human's thermoregulatory state. The metabolic heat rate considers the temperature effects on the metabolism, the heat due to shivering and due to physical activity. The environmental term considers the sensible and latent heat exchange with the environment. And then the far right blood perfusion term considers the heat transfer due to the flow of blood, where the values of the coefficients in the front are determined from empirical models developed by Fiala and Wissler. The right-hand side terms of the bioheat transfer equation are calculated by considering both local regulation mechanisms, such as the Q10 effect on the metabolism, sweating, and blood flow, where Q10 effect refers to a power law equation that describes how a physiological mechanism changes with each 10 degrees Celsius change in temperature. And in addition to the local regulation effects shown on the left here, the model also considers central nervous system regulation mechanisms and their interactions, like shown in the right. So this model allows to predict the skin, tissue, blood, and core temperatures of the body, as well as the sweat rate, with the ability to specify custom sweat maps, like shown in the middle figure, and also shivering and vasomotion. And finally, we can use these physiological predictions to predict the subjective thermal sensation and comfort of a human, where the sensation is defined as how hot or cold something is perceived to feel, and comfort is defined as whether the sensation makes a person feel good or bad. Sensation and comfort is not always directly correlated. For example, a sensation may feel cool, but could be comfortable if the body is hot, such as going swimming in a cool lake on a hot day. So with the 20 body segments of the human model, we can predict how local asymmetries can impact the overall sensation and comfort. Also, differences in physiology can be accounted for, like the gender, height, weight, and body fat, as well as you can specify the activity level as an input in terms of a MET rate, or metabolic equivalent of task, where 1 MET corresponds to a human at rest and is defined as 58 watts per meter squared metabolic heat generation. And then other activities can be related to the MET rates as shown in the table here. Also, different body sizes in terms of population percentiles can be chosen, or you can specify very custom physiologies with custom mechanisms through a text file. Taitherm will also consider the environmental effects on the system, such as the solar loading, the radiation exchange with the sky, and wind convection by using boundary conditions specified in a weather file. So you can model a human in an outdoor environment with asymmetric solar radiation on the body, or some enclosed environment like in a vehicle cabin. For clothing, we have a clothing materials database that's integrated into Taitherm. It has a lot of pre-specified clothing properties, or you can add your own clothing materials and define its parameters, like the thermal and evaporative resistance, a clothing area factor, which accounts for the fact that the clothing isn't skin tight and will have folds, so it will increase the surface area for radiation exchange, and the heat capacity. Many existing human models use a basic clothing model where evaporative heat loss is assumed only to occur at the skin and is computed based on the bulk evaporative resistance of a layered clothing stack, like shown in the figure. And in these models, the layer-to-layer transport of vapor within the clothing layers is not considered, and the humidity within the clothing layer is not known. And this can be a problem because in certain conditions, water vapor diffusion through the clothing layers could reach its dew point, resulting in condensation. And then that condensed liquid could evaporate at a later time from that layer. And these evaporation and condensation phase changes could have a significant impact on the clothing temperature and affect the thermophysiological response and thermal comfort perception. Additionally, if moisture is present within the clothing, the thermal and evaporative resistances may be reduced. Evaporative resistances are often affected by humidity, and thermal resistances are affected by liquid content or sweat. So considering the storage of liquid water or sweat and the diffusion of the water vapor within the fabric layers can improve the accuracy of the thermal predictions. So in order to address these limitations, we developed a coupled heat and moisture transport model, where we modified our heat transfer software to consider the transport of vapor and storage of vapor within porous materials such as clothing. And we did this based on the analogy between heat and mass transport, where for the three modes of heat transfer, conduction, convection, and advection, where temperature is the driving potential for a heat flux, we can write analogous equations for mass transfer, where instead of temperature, now the humidity ratio is the driving potential for the mass flux. And humidity ratio is defined as the mass of water vapor to the mass of dry air ratio. So by using this analogy, the model equations can be written as expressions of conservation of mass and energy on each control volume of the finite volume simulation. So for mass, the net mass moving in and out of the control volume can describe in terms of the mass that moves due to diffusion, which is the first term, plus the mass that moves due to convection, plus any imposed mass, which is being added or removed from the volume by other mechanisms, like active sweating. And in a similar concept, we can write down the energy transfer equation, where we consider both the regular heat transfer and the additional energy transfer due to the energy of the moisture entering or leaving the volume, or the moisture undergoing the phase changes. So we combine this moisture model with the human thermal model by adding moisture nodes to the outer skin and clothing layers for modeling moisture transport. So for each clothing value layer, we consider the thermal and evaporative resistances. And then to consider sweating, the model computes a sweat rate based on the physiology and imposes that sweat on the skin layer. And then we track the evaporation of the sweat and movement of the humidity through the other clothing layers. And more details about the moisture model described in our last year's ICES paper, reference below. We did several validations of this model for clothing and moisture modeling. One was looking at the impact of phase change, where we compared the model's predictions to measurements that were derived from sweating hot plate experiments. And in these experiments, we looked at a clothing stack made of 3 layers, a Gore-Tex material, a polyester batting insulation layer, and capling, which is a fabric made by Patagonia. And to consider to control the physical effects that we're looking at, we separated these fabrics by special films. They're called MVTR films that allow the passage of water vapor, but block the diffusion of liquid water between the clothing layers. And then we sewed in thermocouples, which are these small red ovals, between each of the layers to measure the temperature. This test was done under cool, humid condition that promotes condensation within the clothing. And for the validation, we first fitted the model properties for the dry case as best we could, shown in the plot here. And then we allowed the model to predict the fabric temperatures under the wet hot plate case. And we see that the model was able to predict the locations of phase change and the relative temperature changes of the phase change. So for example, for these layers here, we see an increase in temperature from dry to wet, which means that condensation was occurring in those layers. And then in the capling layer, we see a decrease in temperature in the wet case, which means evaporation was occurring. In another validation, we looked at the impact of liquid accumulation, where we used this 3-layer fabric stack of fleece sandwiched between taffeta. And again, we separated these layers with films that allow passage of vapor but prevent liquid diffusion between the layers. And we ran this test for 18 hours in order to induce enough liquid accumulation in the fleece, which would cause a measurable transient in its thermal resistance. And then for the results, we measured 2 main quantities: the total weight gain due to the liquid accumulation in each fabric layer at the end of the experiments, which is shown in the table here. And we see we are within the error bars of the measurements for the Taitherm prediction. And the other quantity we looked at was the transient hot plate heat flux that was needed to maintain a constant 40 degrees Celsius hot plate temperature. So since the condensation-induced liquid accumulation causes a gradually decreasing fabric thermal resistance, this results in an increase in heat loss over time. So the hot plate needs more power over time to maintain a constant temperature. And that's a way we can measure indirectly the decrease in fabric thermal resistance. So here we also see a good agreement between the modeled and measured results, showing that the model was able to describe this liquid-dependent thermal resistance over time. A few example applications of the model that we worked on. One was evaluating the performance of a personal coolant system. And so this was a cooling vest that is supposed to help cool a human. It was actually interesting that the initial design of the vest was not very good, and the simulation showed that the cooling system was causing a higher skin and core temperature than without the vest, because the vest limited evaporative and convective cooling too much. So then the simulation was used to improve the vest design. Another space-related application was this mechanical counter-pressure suit study, which helped optimize the suit thermal subsystem for Mars EVA, planetary exploration. So the weather on Mars was specified as a boundary condition in Taitherm, and then Taitherm was used to design the suit to enable some evaporative cooling, and it was found that even enabling some small amount of evaporative cooling through the suit wall could be sufficient to prevent heat exhaustion. Also, we've done a lot of work with vehicle modeling, such as you can put multiple humans in a vehicle with unique physiologies, different body sizes, heights, and weights, and then look at their overall thermal comfort and sensation and optimize the HVAC system in the vehicle. So now we'll move on to a more detailed description of a recent study we did on validation of the model for assessing crew-induced loads in spacecraft, and we did present this at this year's ICES conference. So the motivation for this is that it's important to quantify crew-induced loads for ECLS design, and especially spaceflight missions of greater than 30 days require daily exercise, which creates peak loads on the ECLS system. The use of legacy tools for human thermal modeling like MetMan and others that are shown in the chart on the right limits the capability for detailed assessment with vehicles and ECLS models. So we validated our human thermal model for predicting moisture loads as the first step towards integrating the model with spacecraft and ECLS simulation. And this is part of an ongoing effort funded by NASA for coupling the human thermal model and thermal desktop spacecraft models, which will allow to integrate the advanced human thermal results so NASA can design improved life support systems. So for the validation, we used data from 2018 when NASA performed exercise tests to study the moisture loads on the Orion ECLS system. And those tests were used by a group at NASA to improve the MetMan model sweat calculations. In these tests, 30 human subjects were each performing 30 minutes of continuing rowing at 75% aerobic capacity, followed by a 30-minute recovery period. And the environment was around 24 Celsius and 34% humidity. And then the sweat data was obtained by measuring the nude body weights prior to the test, at the end of exercise, and at the end of the recovery period. And the clothing weight was taken before the exercise and at the end of exercise. And also the subjects changed clothes at the end of the exercise. And this test was reported on by Mike Ewert and co-authors at last year's ICES presentation. So for the Taitherm model setup, we specified the boundary conditions reported in the NASA experiments. So the clothing that the subjects were wearing were a t-shirt, shorts, and socks with clothing properties shown here. And note that we also consider the additional clothing insulation that's gained due to the clothing not being skin tight and having folds through this surface area augmentation factor. We also specify the metabolic equivalent of task, or MET rate, as an input. That represents the activity portion of the whole body metabolism for a 50th percentile male, and then Taitherm will automatically scale the metabolism to match the anthropometry. So to do this, we benchmarked the activity level for the reference NASA handbook-sized individual, and then scaled the anthropometry in Taitherm to represent the 5th, 25th, 50th, and 90th percentile males to represent different populations of astronauts. So that ended up being 8.42 MET for exercise and 1.2 for recovery. To model the clothing change that occurs, we removed the liquid sweat that's accumulated in the clothing from the skin and assumed that a maximum of 35 grams per meter squared of sweat remains on the skin. And that's based on a paper by Fiala, which is the maximum capacity of the skin to hold sweat. This is a conservative assumption for modeling the equus loads, since it represents a worst case scenario because it would result in more evaporation than if less sweat was left on the skin. So now I'd like to briefly demonstrate the user interface of Taitherm. And let me pull that up in a second here. Okay. So now you should see the Taitherm interface. This was the model we used for this study. So we have the relatively coarse human body model here. We decided to use a coarse one because it allowed to do more comprehensive simulations quickly. It runs in a few minutes, which was convenient for this study. So for each of the body parts here, we were able to specify the clothing. So first in the clothing properties, we define some clothing material properties such as the shirt and the shorts. So we provide the thermal properties here and also the evaporative and thermal resistance of each layer. And then we can specify the layers here and the thickness of the clothing layers. All of the body part internals of the human body modeling is done in the background for you, so you don't have to worry about specifying that yourself. And then for convection, we typically use a library empirical convection equations based on Fiala's work, which can be selected here, and you just select the fluid temperature of the environment and the flow speed of the air. We then specified the surface properties for the radiation, so the emissivity of the surfaces, and then we can add in any additional imposed heat, liquid flux, or vapor flux that could be occurring. So say if the human was wearing some kind of wearable device, like a watch that maybe was heating his arm, you could add an imposed heat, a value, or a curve that models that, or if there was some water dripping on the human, you could add that as a liquid flux. And then we specify our initialization conditions. Then for the environment, in this case, we're modeling the human in a spacecraft, so it's what we call a bounding box, or just a room with a constant temperature, but you can also use a natural weather environment and select a weather file, and then there are options for Also the background ground modeling, so different types of background soil or concrete where the human might be located. This is more relevant for Earth applications. And then selection of wind model, and there are also options for how to model the sky radiance. And the solar radiance can be either modeled by Taitherm, or you can specify measured solar irradiance values. So then finally, this human is defined as an assembly. You can have multiple humans, which you would define as multiple assemblies, and you could put them in other geometry like a spacecraft or a vehicle. And we defined a activity curve here, which was the metabolic activity based on the human subject tests. As I mentioned, it consisted of a 15-minute rest period and then a high-intensity exercise period followed by a rest period. Finally, there is the human setup dialog, and there's a few accompanying text files that allow you to specify custom physiology properties. So for example, here I'm modeling a 90th percentile human by specifying some details in the text file, and the human model configuration, which gives you different options for how to model the physiology. So what's nice about this, I think this model is kind of the user friendliness in setting it up through the GUI versus some other models require you to modify code or purely use text files. So I just wanted to show that briefly. And now I'll go back to the slides. Okay. So for the results of this validation, the first thing we looked at was total moisture output, because that's something that was measured in the human subject tests. And here's the comparison of the moisture output from the exercise recovery cycles that were measured in the test, then predicted by the NASA MetMan model and predicted by the Taitherm. And for Taitherm, we have several choices of how to model physiology. And one of those choices is the skin blood flow model that is used, where you can use either a model developed by Wissler or Fiala. So we tested both of those skin blood flow models. And on the left, shown the Taitherm results comparison with the Wissler model, and on the right, the Fiala model. We find that the total moisture output predicted by the Fiala skin blood flow model has much better agreement with the test data. It achieved a lower root mean square error than the Wissler model and the MetMan models. So one of the main takeaways is that the choice of skin blood flow model significantly affects the total moisture prediction. And we are planning on doing future work to understand in more detail why that is. The other validation we did was looking at the metabolic loads during the exercise recovery cycle. So these plots show the heat rates in the human body predicted by Taitherm with the two skin blood flow models. So here we clearly see the 30 minutes of exercise followed by the 30 minutes of recovery with the blue line, which is the total heat generation curve. And if you look at the green lines, we see that when we use the Wissler skin blood flow model, we predicted a higher total heat loss than with the Fiala model, mainly during this recovery period. And much of that heat loss comes from the evaporation of sweat from the skin, which we see if we compare the yellow lines. And a few other comments about these plots. The flat regions you see in the beginning here are due to a delay in the onset of sweating in the model. and the slight rising of the heat generation during the exercise portion is due to the physiological changes that occur as the body becomes warmer during exercise. And then we have these sharp drops in the evaporation heat loss, and those occur when all of the liquid sweat is evaporated from a particular body part. So it's an effect of the geometry being discrete. The next plots show the moisture loss for both skin blood flow models. And again, we see higher moisture loss with the Wissler model than Fiala, which is consistent with the higher heat loss that we saw in the previous slides plots, and also with the total moisture loss results that we saw. So to investigate the source of these differences between the moisture loss predictions with the two different physiological skin blood flow models, we plot a few more quantities here. Starting at the top left, we see that the Fiala model predicts a higher skin blood flow rate. And if you look at the next two plots, we see that this caused a lower hypothalamus temperature and higher skin temperatures. Since the body's core is being more effectively cooled by the higher blood flow rate of the blood transferring heat towards the skin. Since the sweat model relies on a sweat signal that's calculated from the skin and hypothalamus temperature, with hypothalamus being the dominant factor, the temperature differences we see here impact the sweat signal of the two models. So with the lower hypothalamus temperature in the Fiala model, we also see a lower sweat signal. So less sweating of the human in that model. And then the higher sweat signal that we saw with Wissler will cause a higher skin wettedness, where skin wettedness is just the ratio of the evaporation that occurs to the maximum possible evaporation that could occur if 100% of the skin was covered with sweat. And then finally, in the bottom right plot, we see that there is a significantly higher skin evaporation heat loss during the recovery period with the Wissler model. And that's mainly due to the higher amount of liquid sweat that remains on the skin at the end of exercise, as we see at the skin wettedness plot. And one thing to note is the only reason we're able to see these, for example, higher skin evaporation during the recovery period is because the model is tracking the liquid accumulation that occurs during exercise and then able to see how that evaporation evaporates during the recovery period. A lot of clothing models, such as the ASHRAE model, will only assume that evaporation is occurring if there is some active sweating, and it will not track what happens to the liquid sweat after the person stops exercising. Finally, we compared the Taitherm results with the MetMan simulation from Mike Ewert's and co-authors' paper from last year's ICES conference. And we find that using Taitherm with the Fiala skin blood flow model gave results that were closer to the MetMan results than using the Wissler model. The Fiala model predicted a higher sensible heat loss than Wissler, and this was likely due to its higher mean skin temperatures. We also saw that the latent heat results for Fiala and Wissler are actually very close during the exercise portion, but start to differ during the recovery portion, where we have higher latent heat loss by Wissler, as I mentioned before, that's caused by the higher liquid accumulation and sweating that is seen. The water vapor output behavior is exactly the same as latent heat, since it's directly related to the latent heat through the enthalpy of vaporization. And then both Taitherm models predict lower latent heat and water vapor output than MetMan during the exercise portion. And that difference could be due to different assumptions about the clothing evaporative resistances or the convection coefficients between the Taitherm model and the MetMan model. We also saw that Both Taitherm models predicted an earlier appearance of the sweat on the skin and clothing than in MetMan. And that also could be due to differences in the evaporative or convection coefficients that were used in the models. And finally, if you look at the table of total metabolic loads over 1 hour cycle, you find that Taitherm results with Fiala model are much more similar to MetMan than Wissler model. And I think especially promising is this last box of the total moisture output, which was very close to the MetMan model. And one thing to note is the MetMan model was specifically tuned to this human subject test data to improve the model. And we ran the Taitherm model without any tuning, using just the default coefficients. So for conclusions of this study, we saw that the model's total moisture output prediction was within 23 grams of a linear fit through measured values from the human subject tests when we used the Fiala skin blood flow model without any model tuning. And we saw that the choice of the skin blood flow model significantly affects the HTM's results, and showed how looking at the thermophysiological quantities can help us understand the origins of some differences in total moisture loss predictions. For our ongoing and future work, we're working on a phase 2 NASA SBIR for co-simulation for assessments of crew-induced loads and ECLIS systems. So this human thermal model that I described here is being coupled with thermal desktop, and the thermal desktop will be computing the heat transfer between the spacecraft exterior and the Earth and Sun and outer space. And then Taitherm will be computing the details of the human thermal physiology and predicting the crew-induced loads. And we're developing a coupling applications to allow for easily coupling of these two softwares and allow for integrated analysis of things like CO2 levels, body core temperature, humidity, the heat transfer, and the induced loads to help design the ECLIS system. So that's the end of my presentation, and here is our contact info. Thank you for your attention, and I can now answer any questions.
Thank you, Timofey. That was fascinating. There are a few questions. Actually, I submitted some questions in the chat, and I would encourage anybody else in the audience to please submit the question. But Timofey, if you click on the chat, that will open up and you can see the questions.
Okay.
And I think you did discuss this, but my first question, just to show you where we're at in the chat, was: does the model account for cooling due to blood circulation? So if you wouldn't mind talking a little bit more about that and how you model that and how you maybe anchored that model and how that affects the cooling. Because my understanding of cooling in the body is that the blood circulation helps cool the body, perhaps by transporting energy away from hotter sections of the body to cooler sections of the body.
Yes. So we have a blood flow model. There's actually 2 blood flow models. I was mostly here focusing on the differences between the skin blood flow models that we use from Wissler and Fiala. We also have an intersegment blood flow model, which there's also a choice between Wissler and Fiala. Those were the 2 main physiology experts in the field and in the literature that developed models. So the intersegment blood flow model models the flow of blood between the 20 segments of the human body that we have, and then the skin blood flow model will model how the blood flows from the interior arteries and veins out to the surface of the skin. And then we also model thermoregulation mechanisms like vasodilation and vasoconstriction, where the human body will dilate or constrict blood vessels in response to cold or hot environments to either help move more blood towards the extremities or keep more blood towards the core to keep the core at warm enough.
Okay, quick follow-on question to that. In your you mentioned about how modeling the tissues and so on. Is your modeling based on the actual geometry of and configuration of the tissue, or is it more of an empirical type modeling where you've rather than actually modeling the actual geometry and material properties and so on, are you doing some? Could you talk about that, because that's kind of fascinating. Does that make sense? What my question is.
Yes, I think that makes sense. So we do still use somewhat of a cylinder-based layering approach where each body segments will have different amounts of layers depending on what makes sense. So, for example, the core will have some layers corresponding to the lungs, and the hands would not. But these layers, each layer has some tissue material properties based on the literature, which allow to model accurate heat transfer. But it is a homogeneous layer across its segments, so it's not, in this particular model, it's not like a three-dimensional, physiologically accurate, like we don't model the organs specifically, the geometry of the organs and things like that. Although in another work, we are working on full three-dimensional modeling with a voxel approach where we are modeling the human body based on MRI scans with all of the organs, but that kind of model is much more computationally expensive and in many cases not necessary for the types of study you may want to do.
Okay, that makes sense. Next question: during the model validation, you mentioned that the code automatically scales metabolism to match the, and I'll try to pronounce this properly, anthropometry. Would you please explain to me what that means?
Yes. So it can be a little different than some other models. We use the metabolic rate as an input, and that input is supposed to correspond to the metabolic heat output of a 50th percentile male based on the genetic population. Then through a text file, you can specify a different anthropometry, which is the body size, body fat. So you can select, say, a 75th percentile male, which has a greater height, and you can also select different body fat amounts. And then internally, we will take the input that you give for the 50th, that's calibrated kind of for the 50th percentile male, and Taitherm will automatically increase the metabolic heat output to match the anthropometry that you select. And it will also adjust all of the other coefficients that are controlling the physiological mechanisms like vasodilation, vasoconstriction, shivering, and sweating to match the anthropometry that you select based on a scaling. There's also an option to override that, and if you know the detailed physiology properties, say you want to model a specific astronaut and you've measured how their metabolism and physiology works, you can override all of those coefficients in a text file and select your own metabolic properties. but most users typically don't have that kind of detailed data, so they use the automatic scaling.
Okay, well, thank you. That makes sense. And are you working on any type of modeling that models the body in a spacesuit in a vacuum environment where outside of the spacesuit you don't have evaporation, but you'll have evaporation in the spacesuit? And I don't know a lot about spacesuits, but I believe a lot of them have some type of circulation cooling through the spacesuit itself.
Yeah, that's something that we hope to be able to do with our coupling with thermal desktop that we're working on. We haven't yet developed such models, but the idea is that the human body would be modeled in Taitherm, and then the spacesuit, where there's already existing spacesuit models that were developed in thermal desktop. So we would insert the human geometry into the spacesuit geometry in thermal desktop, and then exchange boundary conditions of heat transfer and moisture transfer between the human and the spacesuit environment, and allow to model that.
All right, thank you. And do these models consider differences in human internal processes based on positions, for example, sitting or standing?
There is currently a limited amount of, there's basically, two positions right now. There's what we call a sedentary position and I believe a standing position, which changes the standing position puts more metabolism into the legs due to the muscles being used more. But it's a little bit limited there. If you want to model more detailed positions or exercise where maybe the arms are performing some exercise, you would have to modify the physiology file where you can alter the distribution of metabolic heat throughout the body to account for different activities.